Hello, my name is Socrates. I'm a PhD student at the University of Cambridge. My research topic is the blast response of laminated glass, and I'm working together with Dr. Talbot and Dr. Overend. So before starting the presentations, I would like to gratefully acknowledge the support from the Engineering and Physical Science Research Council and the Institution of Civil Engineers for assisting me and funding my research. Despite the significant consequences from explosion incidents, as can be shown from the damaged building in Oklahoma in 1995 from a terrorist attack, the regulatory requirement for including blast design load as a separate structural design condition is often limited to the oil and gas and nuclear power plants. In the oil and gas, the requirement arises due to the multiple accidental explosion incidents that have been observed both in onshore and offshore petrochemical facilities due to the large presence of hydrocarbon content. In nuclear power plants, explosion incidents are less frequent. However, due to the severe consequences of releasing radiation in the environment, structures are requested to be blast resistant in case of loss of containment. In buildings and other civil engineering structures, regulatory compliance is often achieved by performing a robust design, that is, preventing disproportional collapse, and without specifically considering explosion scenarios. However, there's an increased frequency in terrorist attacks observed recently that has intensified the requirement for blast-resilient buildings in the commercial and residential sector. As a result, building facades that are traditionally considered architectural elements must therefore act as a first barrier of defense in case of a blast event, preventing the blast waves from penetrating the building interior. As can be seen from the load path diagram, cladding elements will resist first the blast pressures before spreading the load to the structural frame. Achieving a design with a blast-resilient glazed facade is a complicated problem. Typical monolithic glazing products, such as annealed, heat-strengthened, and toughened glass, are brittle and have no reserve capacity beyond fracture. In addition, many glass-related injuries have been observed in blast events due to the projection of glass shards at high velocity. Therefore, laminated glass panels that fail in a more ductile manner and can reduce glass-related injuries as glass fragments remain attached to the interlayer are often preferred for blast applications. The focus of this presentation will therefore be on the blast response of laminated glass. This is a problem that is a multidisciplinary and has attracted significant research efforts recently. A literature review on this topic can identify numerous finite element analysis, many equivalent single degree of freedom methods, and some analytical solutions. However, if you compare all of these methods with each other, it can be observed that there are many discrepancies in the assumptions considered in these analyses. Despite that, all methods demonstrate good agreement with experimental results. Therefore, in our research, we have decided to take a different approach, and rather than developing one more tool that can reproduce the experimentally measured peak displacement time history, we have decided to take a more first principle approach and therefore break down the complex blast response. We therefore aim to assess independently the effects of high strain rates, the influence of in-plane restraints, the inertia effects due to the dynamic loading, and the plate geometry. This will therefore aim to start as a starting point with a laminated glass beam simply supported, which is considered a more well-defined problem that has been experimentally validated, and from there assessed independently each one of these events. This aims to bridge the knowledge gap between the well-controlled small-scale test done at the material level with the more complex that include many uncertainties full-scale blast tests. As this is still the start of my research in the PhD, this presentation will only focus on the high strain rates and in-plane restraints and ignore for the time being inertia effects and only consider simplified beam models. At the start of this presentation, I will present a small brief literature review on the influence of high strain rates on the material properties of both the glass layers and the interlayer of laminated glass panels. I should mention that I will only be talking about PVB in this case as an interlayer. The high strain rates affect the response of laminated glass panels both in the pre-fracture and the post-fracture response. In the pre-fracture response, the interlayer can be assumed as an elastic plastic material with strain hardening. This allows significant simplifications when developing analytical models, especially when compared with low strain rate analysis that requires full viscoelastic analysis. The elastic plastic with strain hardening response has been observed in many publications and that have performed tensile tests at high strain rates. The glass layers are also affected by the high strain rates, as cracks require time to grow. This has been observed both experimentally from multiple blast tests that have defined higher fracture strength values, and also demonstrated analytically by extrapolating the low strain rate values to high strain rates using Brown's integral. In the post-fracture response, the behavior of the interlayer is affected by the attached glass fragments, resulting in a stiffening effect. This has been discussed in many publications, and mainly, I think, by my next speaker, Roger, I think, Galuppi and Roger Carfagni. I think one of your presentations has included that, and Dr. Galuppi, I think, mentioned it yesterday in her presentation. So this includes a method to determine the stiffness of the composite material in the post-fracture response. However, as the aim in this case is to present simplified models, and we have tried to avoid in this stage determining the lamination length, we have at this stage decided to use material properties that have been derived from experiments. So we've used the experiments performed by Hooper, and they have defined in the post-fracture state yield strength values, strain failures, and initial Young's modulus. These were tensile tests performed at high strain rates at pre-fractured laminated glass specimens, including a uniform cracking pattern of 10 millimeter length of fragments. It was also noted in these tests that the stress-strain response of the composite interlayer with attached glass fragment is elastic perfectly plastic rather than elastic plastic with strain hardening as observed in the behavior of PVB alone without the attached glass fragments. Following the definition of the enhanced material properties of both the glass layers and the interlayer due to high strain rates, we have developed some simplified analytical models to assess the structural behavior due to these enhanced properties. In all cases, we're going to consider simply supported laminated glass beams. Starting with the first stage, which is the unfractured stage, we have considered a fully composite bending analysis for laminated glass. The assumption of a fully composite bending response will be verified later in the presentation. When the glass layer that is in tension first fractures, the second stage will commence. At this point, the residual bending capacity is provided by the remaining unfractured glass layer and the interlayer. It is, however, considered that the contribution of the interlayer is negligible due to the higher stiffness of the unfractured glass layer. The third stage considers that both glass layers have fractured, and the composite bending response is provided by the attached glass fragments that come into contact and generate compressive stresses, and the interlayer in tension. In all three cases, the bending moment capacities have been derived by transforming this composite material into an equivalent glass or PVB section and calculate the moment capacities assuming plane sections remain plane. The equivalent curvature capacities have been defined assuming linear elasticity in these stages. Stage 3 is valid as long as the interlayer does not yield. Even though this does not refer to true plasticity, as PVB is a viscoelastic polymer, we refer to yielding as the observed reduction in stiffness in the material tests that can be seen that have been observed. Therefore, following the yielding of the interlayer, as more loading is applied to the structure, the strains will keep increasing. However, as the material law described is elastic, perfectly plastic, the stresses cannot exceed the yield value. At this stage, therefore, the plastic neutral axis will shift upwards to accommodate this change. Eventually, failure will occur when the attached glass fragments fail in compressive crushing. At this point, we can define the ultimate moment capacity by taking moment equilibrium about the plastic neutral axis. The curvature capacity at this stage can be defined by still assuming plane sections remain plane and a linear relationship for the strain diagram. A similar approach has also been performed in some other publications that refer to the post-fracture response of laminated glass beams with SGP, which is a stiffer interlayer. So the approach we're trying to introduce here is to say that due to the high strain rates, the stiffer response of the PVB will be similar with the experimentally observed result of laminated glass beams that have a stiffer interlayer, sorry. So once the moment capacity in stage 4 has been exceeded, a plastic hinge will form. If it's a simply supported beam, this will result in a collapse mechanism. For different boundary conditions, further plastic hinges may also form. Following the definition of the high strain rates effects on the structural response of laminated glass beams, the next topic is to identify the influence of in-plane restraint in laminated glass panels. This is a common requirement for the blast design of laminated glass panels, that they're restrained in in-plane direction in order to provide a higher capacity of the panel. In this presentation, we have assumed for simplicity that we will have pin supports that are actually restrained in order to be able to compare directly with our results for the simply supported models derived before. In this case, instead of having only bending moments, we will have the composite bending and membrane action under large deflections due to the stretching of the panel. This will complicate significantly even the elastic stages, as due to the contribution of the membrane forces, we will now need to solve the nonlinear differential equations. In the plastic stage, the combined bending and membrane stresses cannot exceed the yield stress due to the adopted elastic perfectly plastic material law. In this case, we need to define a yield condition in order to ensure that the material law is not violated. This will allow us to determine the relative contribution of bending and membrane forces. In this equation, M and N refer to the non-dimensional bending forces and bending moments and membrane forces with respect to their capacities. I must apologize for some of the large equations that are going to be presented in this slide. The aim is not to follow them at this stage, just to give you a quick review of the outcome of the work done, and you can find a full derivation in the paper. So following the derivation of the yield condition, the upper bound theorem of plasticity can be applied to derive the collapse load. In this case, as we have large deflections and composite bending and membrane action, the external work done is absorbed into both bending and membrane strain energy. At this case, we have assumed the same collapse mechanism as for simply supported beams, also for the actually restrained case. This is a common assumption that is considered in the plastic analysis. However, this means that all the plastic bending and membrane strains will be localized at the plastic hinge length. However, as the deflections keep increasing, the plastic hinge length will also extend and eventually reach to the entire panel, entire beam length when we have a pure membrane response. Finally, we can define the collapse load at which tearing occurs. This can be achieved by equating the bending and membrane strains with a tearing failure at high strain rates that was previously defined. It should be noted that this only refers to tearing strain and does not account from cutting from the attached glass fragments. To quantify the effects of the in-plane restraint and the high strain rates, we have implemented in a numerical software the simplified analytical models presented here. The first step was to check the assumption of composite bending response. So in this case, assume for the prefracture response at stage 1. So in this case, we compared the deflection under simple bending with the enhanced effective thickness approach developed by Dr. Galuppi and Royer Carfagni. And we can found that this is valid for blast design due to the higher shear modulus of PVB, especially for the larger lengths, and therefore shear deflections, as commonly considered in practice, can be ignored. Also, we have plotted the moment curvature capacities for each stage to assess the influence of high strain rates. In the pre-fracture stage, we can see that the moment capacity is significantly enhanced. I should mention that the low strain rate moment capacity has been defined as if there is no transfer in the shear interlayer, which is not exactly accurate, but just for simplification, we have assumed that each of the glass layers bends independently. In the second stage, the assumption that we previously made that the contribution of the interlayer when we have only one glass fragment is negligible is actually confirmed, as we can see that the two lines are parallel to each other. In the case of the high strain rates, we have assumed the transformation method, where both the unfractured glass layer works together with the interlayer, whereas for the case of low strain rates, we have assumed only the unfractured glass layer to behave on its own. The enhancement of the moment capacity is entirely due to the higher fracture strength of glass under higher strain rates, as discussed earlier on in the literature review. Finally, in the post-fracture response, stages 3 and 4, we have plotted the moment capacities, and we've only plotted the moment capacities for higher strain rates, ignoring the moment capacities for low strain rates. This is, as we have discovered in many publications that have done tests under low strain rates for laminated glass beams and have found that there is no post-fracture capacity. An interesting comparison can be made with reinforced concrete, which is also a brittle material that is reinforced with a more ductile material. Bending moment capacities are calculated in an equivalent manner. However, in reinforced concrete, the moment capacities keep increasing with the stages. However, in laminated glass, the moment capacity is decreasing with stages. Therefore, very simple tools such as the upper bound theorem of plasticity that utilizes yield line patterns to design reinforced concrete slabs cannot be applied for laminated glass beams that are actually unrestrained. Next, we assessed the influence of actual restraints for each stage independently. So in the first stage, which is the unfractured stage, we can see that it depends on the span length. So we consider two separate spans, a short one that is 200 millimeters long and a long one that is 1 meter long. So obviously, as expected in the short span, the membrane contribution is negligible, while for the long span, we can see that membrane action is participating in the response. I should mention that these deflections have been derived by solving the nonlinear differential equation using Galerkin method. In the second stage, where now only one glass layer works, we have small contribution of membrane action even in the shorter span, while in the larger span, the membrane response dominates the response. The membrane action dominates the response. Finally, the results of the plastic analysis highlights the significance of actual restraints. Here we have plotted the non-dimensional collapse load versus deflection. This indicates that we have a significant enhancement in the collapse load due to the effects of actual restraints compared to actually unrestrained laminated glass beams. This also shows that the collapse load in the post-fracture response when actual restraints are placed give higher loads compared to the capacity of the intact laminated glass panel. This is also something that has been observed in multiple blast tests that can go into deflections way beyond after both glass layers have fractured. So finally, I would like to inform you that following the development of these simplified models to assess the influence of high strain rates and in-plane restraints, we would like to perform some experimental tests to validate these models. So at this stage, this is very beginning, so we haven't started doing any testing. So obviously any support, advice, or input from industry is very much welcome. In addition, we're also working on expanding these models to assess independently the effects, the inertia effects, and to extend it to a more complicated plate geometry. Thank you very much.
Thank you. Sorry. Thank you for the interesting presentation. We have time for 1 or 2 questions.
So thank you for your presentation. It's obvious you are very well prepared. So congratulations on that.
Thank you.
You've done a lot of review of the literature and to understand and to take on this project. And here at the end, you talked about input from industry on validation. But as you have looked at that part of the literature and all those tests, what do you think and what would your strategy be for validating these models?
So when I'm talking about input from industry is more to help perhaps perform these tests, because my background is more analytical work. I don't have myself much experience yet in performing experiments, and I'm sure this is something that comes a lot with experience and what to do, what not to do. I think the trouble we're having at this stage is if we want to assess independently the individual contributions, we need to also uncouple the responses as well in the experimental work. So therefore, we want to do simple experiments and slowly start from the static response of laminated glass beams and do theory tests to go all the way to the more complicated full-scale blast tests. So we need to be very careful and try and find experiments that also uncouple the behavior. So for instance, doing high strain rate tests may also result to inertia effects. So it does not help in terms of uncoupling these 2 responses. So this is obviously something work in progress. So thank you.
One more question? Apparently convinced everybody. Thank you very much, and good luck with the presentation.